Okay. Last time we went through the basics of relative acceleration. This is the base. This is the summary of that. In a problem of a problem related to relative acceleration, the number of equations you can obtain is equal to the number of particles moving. Right? Suppose that, without reactions, if you get, you can get exactly this many equations, or number of equations should be uh, the number of moving particles, and you can obtain such equations without reactions. So, number of accelerations plus number of tensions is equal to the number of moving particles. That means you have exact number of equations, right amount of equations to find these. Then what you need to do is that apply F equals ma or Newton's law exactly n times. And it's the number of moving particles. So you can afterwards you can solve those equations. The second type is this. Say number of moving particles, so the number of equations is n. However, number of accelerations plus tensions is just one above that. It is n plus 1. Therefore, you don't have enough equations to solve them because you have n equations, you have n plus 1 variables. So you need an extra equation. In fact, there should be, one extra equation is hidden, but we cannot see it. Therefore, you have to use uh, derivatives to find an extra equation. We went through something like that last time. Then apply Newton's law exactly n times because you have n number of particles. With that extra equation, you have n plus 1 equations. So job done. You can find the unknowns easily. Okay, we'll take this problem. Now, usually these problems are little complicated. Here you have four objects, one, two, three, four. This is a pulley. So we'll first mark the accelerations. Since we need to uh, capture everything, uh, I'll draw the diagram somewhere here. But what you need to do is that draw the diagram and write the equations just below that. I'll do it around the diagram so that it's a little bit easier for the for to get everything captured by the video. So this is M. This is also M. Then this is placed on a horizontal surface with no string attached. And this is alpha. The mass of this is 2m. Now you can, you don't even have to, okay, this 2m. Uh, we'll name this, let the wedge be q. Now we'll have to mark the accelerations. Let this be, here one arrow is sufficient, capital F. Okay. Now this is P1. I'll take this as simple F1. But this is also simple F1 because at the end of, this is, P2 is attached to the other end of the string, right? Since the string is non-extensible or inextensible, this is also F1. I'll take this as F3 just to avoid confusion because it is P3. So I denote it by F3 even though there's no F2, right? Or I can simply denote it by simple F. So no preference is given over 1 or 2, P1 or P2. Now, I have to distinguish between these two. So this is P1, P2, P3. This is Q. So the acceleration, right, of 2m relative to the Earth. Acceleration of 2m relative to the Earth. So that is simple F. These are the accelerations related to Q or the wedge. You know, when you apply F equals ma, the Newton's law, you have to apply it. I'm sorry, the acceleration should be that relative to the Earth, right? So that's why we are striving a little hard to figure that out. So now, uh, okay, we, I mean, this F1, simple F is this acceleration of P1 relative to 2m. It is this way. If, and it makes an angle alpha with the horizontal. Acceleration of P2 relative to 2m is F, but it's a horizontal acceleration. This. And then you have another one, that is the acceleration of P3 relative to 2m, which is again in this direction, and it is F3. Now, we don't need them. We need the accelerations relative to the Earth. Now, for this, for P1, you can write it like this P1 relative to the Earth, which is, you can put 2m in the middle, like vector notation, then 2m E. Now, this is, everything is known. This is, I mean, P1, comma, it is this. So there are exactly two components here. The other is this. Now we can go for P2, comma, E. Or in other words, that's the acceleration of P2 related to the Earth. But those are not connected. Therefore, you have to write it via 2m, the wedge. So you have that. Now this is simple F. This is the other way around. If you want, you can, since they are exactly opposite, you can do it like this. No, we'll leave it in that way. Hmm. Or you can have it like that. If you mark the acceleration in this direction, this is minus F. But if you do it in the other way around, then capital F minus simple F. Now this is simple F minus capital F. We have to do one more. Shall I do it here? This will save space. P3, comma E. Now this is again F3, like similar to the case of P2. We'll mark it in this way. Simple F, sorry, capital F minus simple F3. I'll do the same thing here. Now we'll write equations. Now to write equations, we need to draw it again. I mean, could have drawn, I mean, could done with the same diagram. But once you figure this out, it would be easier to redraw it and do the problem. Huh? We'll do it here. I need some room here, more room here, I would say. Otherwise, the diagram will be a little bit congested. Bring force these weights all the way down. Otherwise, it will be too congested. If you mark them there, up there, mg. Now this is the weight of the wedge. Then there's a reaction between the table and the wedge. I'll take it as R. right? Now, there are reactions between these guys. Since it is P1, I label it like this. Here you have a reaction S2. This is an internal reaction. There's a reaction between these two. Like now, there's another one. S3. This is S3. Now look, this S3 is the reaction or the force from this particle on the wedge. This is the force on S3 by the wedge. So it's like that. Now we'll, basically that's it. Now we'll mark the accelerations. We better use two double arrows. Otherwise it will be, hard to distinguish between the forces and the accelerations. Now, this has two components. One is due to the wedge and the other is F3. Two components there. Okay, here, this also has two components. Look. So I have to, now this on the wedge. Therefore, this is the acceleration of the wedge. And to this side, this is the string. You have F. To this side, you have F. It's kind of extremely complicated, right? And there's a tension as well. T. I think I wish I had more room here, but it's okay, we can handle it. Now we'll write equations. Now we have to write 4 equations. Hold on. How many variables? Okay, 1, F3, 2, simple if the third one, and the tension. 1 tension and 3 accelerations, so altogether 4. However, fortunately, you have 4 moving objects, 1, 2, 3, and 4, P1, P2, P3, and Q. So 5. You can simply write 4 Newton's law. I mean, you can apply it if you could say me 4 times, then solve the equations. Now, how can you write them? You have to write them without getting these reactions involved. So we'll start with an easy problem. Take this, easy case, or this. No, I'll go for that. P3. So applying F equals ma, this which way? This way. Because its acceleration is in this way. For P3. Now, if you could say me, what are the forces? There's no force because one is the reaction, the other is the weight. So no reaction, nothing, sorry, no force acting on that. So the number forces is 0, net forces. The mass is m times the acceleration. What is the acceleration? This is F3 because we are applying it in this way. There's another component which is capital F. Okay, what does this mean? Since m is not equal to 0, you can divide it by m. So capital F is F3. That's easy. Right? Now apply 2 equations to these 2. And we need to find capital F, right? Okay. We'll apply an equation to P2. Again, you can apply it in this way because its main acceleration is simple F. And if you apply horizontally, the S2 will not be involved in the equation. Now, what are the forces? This weight, it's not involved if you apply the equation horizontally. The reaction is not getting involved, but this tension will be there, T. It is in this way, m times the acceleration, simple F minus capital F. We can leave it like that. Now, we'll apply an equation along the surface, um, along this way, because we have to get rid of S1. So we'll apply an equation, the Newton's law this way for P1. I did write P1, P2, P3. If I won't, I would write it like this. It will be too congested if I write it here. This P1, no? It's this object. Now, this is, sorry. Now, weight is here. Now, S1 will not be involved, but mg will be there. This is alpha. This angle right there is 90 minus alpha. So it is mg cos 90 minus alpha, which is mg sin alpha. Mg sin alpha is the weight component. It comes from mg cos 90 minus alpha. Now T is in the exact opposite direction. Mass is m. Now what is the acceleration? Simple F is in this direction. There's another component, capital F, and this angle is alpha. So it is capital F cos alpha in this direction. Right? So you have this. If now our objective is to find capital F. So when you find these accelerations, I mean, now there are two kind of variables, tensions and accelerations. Now you have to find accelerations first, not the tensions. If a wedge is involved, you have to find you have to find the accelerations first, not the tensions. So whenever you have tensions, you have to remove them from the equations, right? Anyway, we'll keep it like that. This is the third equation. Now, if you want, you can remove the tension straight away, because the fourth equation for the wedge, uh, a tension will not appear in there, right? A tension will not appear in the equation for the wedge. Therefore, if you want, you can eliminate T at this point. So rather than labeling it as 3, because we want to have a simplified version of this version. Otherwise, if you have 4 equations, then you have to eliminate one after the other. It will take some time. Therefore, since this is the only tension you have, you can eliminate this. How? Now, from 2. I mean, that's one way of doing it. Or you can leave it as the third equation, then first you remove T, then you take care of the other stuff. That's also possible. Na? So I'll do it in a more primitive way. It's okay. This is the third equation. Now the fourth. Now fourth, I mean, you cannot apply an equation to the wedge itself, right? You cannot. The reason is, if you do that, you have to apply the equation horizontally. So R will not appear, S2, S3 will not appear, but S1 will be there. We don't want reactions to be there. Therefore, you have to apply the equations for the system, not for the wedge itself. Right? Now, we applied those, so far we have applied the equations for the particles, but you cannot apply the equation to the wedge because it is connected to everything. Therefore, now you apply the equation for the system. Now, the only reaction between the outer world and the system is R, because it's placed on the table. So the reaction between table is the only thing which comes from outside, and these weights will be there. But if you apply the equation horizontally, R will not involved. R will not be involved. Therefore, we'll apply F equals ma horizontally, then R, you can get rid of R. Now, you might ask me, so what happens to S1? Now, S1 is an internal reaction. These two will go away. S2 will go away, even the tension will go away. the pulley, tension, the string, and everything is considered as, considered to be in that system. So entire thing. Hmm. So if you apply F equals ma for the system, this is what you get. Now, what are the forces? S1, S2, S3 are internal reactions. T is an internal thing. So those things will not appear, and these weights will not appear since we apply horizontally. R will not appear as well. So nothing will appear in that equation. So there's only zero force. What about MA? Now, how do you apply F equals MA if you have several objects? We have never applied it like that. Now, this is the first place we are going to see something like that. So there are four masses. It is simply F is equal to sigma MA, means MA product for every piece, every moving object, you have to take MA product. MA product. Right. So what about this? Wedge. The mass is 2m, its acceleration is f in that direction. Then we'll go for this p1. It's simple m times, this way. Capital F minus r. This should be resolved. This angle is, if you resolve it horizontally, it is f cos alpha, because this is alpha. Don't mess it up. It will be too complicated. Then simple F minus, capital F minus simple F cos alpha. You can see it from here. Here. If you resolve it like that, capital simple F cos alpha. It is in the other direction. Now we go for P2. Again, the mass is m. It has two components. So I am applying the equation this way. So capital F minus simple F is its acceleration. Now there's another piece. This. So simple m times capital F minus F3. Now start getting rid of these things. First, F3 appears only in these two places. So you better replace it at once. Then there won't be any worry afterwards. You don't have to use the equation 1. So from 1, capital F is simple F3. Oh, you can replace simple F3 by capital F. So this should be 0. Because you have the same thing there. It is 0. So it will be like this afterwards. And at the same time, you can divide it by simple m, but we'll do it later. It is this, because this will be 0. So you don't have to write it. Now, you can divide it by m if you want to. And now you need to still there will be two variables, simple F and capital F. Now you need to do something for that as well. Now, you can wait there. Anyway, first we'll divide it by simple F. 2F plus F minus simple M cos alpha plus, now we divide everything by M, simple M. So you have this. Now you can come up with an equation. After that, we don't need the diagram. Now it is simply algebra afterwards. This is 4F. I can do it here. 4F. Now, from these two, you can pull out simple F. You have cos alpha plus 1. I write 1 plus cos alpha. Now I have to label it as 5. Now we don't need 1. Yeah, 4. I'm sorry, 4. 4. Now from these two, I could have done it earlier, I told you, right? You can eliminate T simply by adding these two. Oh, you can substitute that piece here. From 2 and 3, you can come up with another equation. We'll do it now. Could have done it earlier though. Harish, right? Because T appears only in these two. So like in F, like the case of F3, you could have straight away eliminated that. Okay, if you add these two, the left-hand side, mg sin alpha will be there, minus plus t and minus t will go away. So from these two, you get mg sin alpha in the left-hand side. Now, when you add these two, again, that won't be very complicated. You have m times simple F minus capital F plus this guy. I'm adding these two. M times simple F minus capital F cos alpha. Now you better divide everything by M. So it will simplify this a great deal. Now you have, now this is 2F. Again, the same thing. You can pull out capital F from these two. You get 1 plus cos alpha in the bracket. Now you need to, solve these two. Sorry, you have to solve for capital F. I mean, there are only two equations remaining. How can you do that? Now you need to eliminate simple F. You have to find capital F. So I think you could have used this. Right now, what is okay? You need to get rid of simple F, right? I'll just go one more line here. Right? You can write simple F in terms of capital F, or at least I write this in this side so that it may avoid any confusion here. I label this as 4 because we need to eliminate simple F. Now, what is simple F? Simple F is 4F divided by 1 plus cos alpha. Simple F is 4 capital F divided by 1 plus cos alpha. Now, if you replace this guy by that, the only variable remaining in that equation will be capital F. Now, you have two equations. Now, it's a simple case. You have two equations and two variables because the other variables were eliminated. F3 was the first variable to be eliminated. Then we eliminated t. Now, two remaining. Now, capital F and simple F. Now, simple F is 4F divided by this. So, from equation 4, I'm going to replace capital F by, sorry, other way around, simple F by capital F. And by doing so, I will get an equation consisting of one variable, and that's it. That's a variable we. So, 4F divided by 1 plus cos alpha. It's kind of interesting, it's kind of challenging, little challenging. Not that, it's not that difficult though, but it has certain amount of complexity, uh, first we have to deal with these things. Then, the diagram, initially that's fine, but the diagram has some complexity. Even though it is complex, you can, if you slowly deal with this, without getting panic, I would say, you can easily do the problem, but here you have to eliminate one after variables, one after the other, the unnecessary variables. And on the other hand, these days, uh, due to the degree of difficulty, or I would say, I don't say difficulty, degree of complexity involved with the problem, they sometimes ask you to write the necessary equations to find something. So in fact, you don't have to solve it. The problem is this. Earlier, before 2000, this was a 30-minute problem. So a candidate has enough time to solve the problem within 30 minutes. But now it's a 13-minute problem, not 30, it's 13. Then we don't have enough time to solve this. Therefore, sometimes they ask you to Just write the equations. So anyway, we'll go ahead with this. Now we'll multiply everything by 1 plus cos alpha. I'll put 1 plus cos alpha like this. Then if you multiply this by 1 plus cos alpha, you get 8f. If you multiply 1 plus this by 1 plus cos alpha, you get this. Now you can pull out f from the right hand side. You get 8 minus 1 plus cos alpha quantity squared. So this is the acceleration of the wedge. Now, in fact, once you know the acceleration of the wedge, you can find everything. For example, you know the F3. Hmm. If you, if you substitute that expression here, you can find simple F. If you know both simple F and capital F, you can find T. So you know everything. Hmm. So it's not a big deal. Once you find one of them, then you know the rest. Usually, capital F is the first variable to be found because that's the easiest one because that equation is almost everywhere. Oh, sorry, that not that equation. That variable is almost everywhere. So it's hard to eliminate capital F. No matter what you need to find, first you need to find capital F. Then you know everything. Okay. I'll give you a little time to take for you to take this down. Then we'll do another problem. Right. Right. This kind of a simpler version of this, sorry, P2. So the mass of P1 is m, mass of P2 is 2m. I'll take this as 3m. Again, when the system is released, find the acceleration of the wedge. We'll find, I mean, wedge related to the Earth, I would say, but it's clearly, if you just mention it as the acceleration of the wedge, it is simply the relative to the Earth. Also find, right. Okay. First, let's draw the diagram first. Here, you don't have to write all the, I mean, indicate all the forces involved, right? Now, we can take the, okay, they are placed like this. And this is Q, or 3. We can treat it like that. Now, the acceleration of the wedge, or you can write Q or 3m, related to the Earth is this. Either you can, I mean, you can, if you want, you can name it as Q. Now, the relative acceleration of, or the acceleration of PM related to 3m. 3m is the wedge. It is in this way. The acceleration of P3 relative to 3m is F. It is a simple F, it's a horizontal acceleration. Now we'll go ahead with the other two. What is that? Because to apply Newton's law, you need the acceleration of a particle relative to the Earth. Now we'll go for P1. Now write, I mean, these are not directly connected. Therefore, you have to write it via 3m, like according to the vector notation. Now this is right there. And the next one is capital F. You can leave it like that. Now the acceleration of P2 related to the Earth. Do the same thing. Now acceleration of P2 related to 3m. It is simple F, or it is like this. It is this way. And the other one is in the other way. Therefore, if you name it like this, it is capital F minus simple F. Like that. Now we can go ahead and consider the full, this capital F, sorry. We'll consider the diagram with all the forces and everything, reactions, tensions, right? This kind of simpler than the previous problem. So I'll draw it here. These are the weights and the tensions, and I missed one. It is the weight of the wedge. Now we'll mark the reactions. This is P2, this is P1. P1 means this object. This is the this Q or the wedge. Now we'll mark the accelerations. Tensions are marked, all the reactions are marked. One reaction is missing. It's a reaction between the table and the wedge. That's in fact the most important one out of these three anyway. Now the accelerations with the double arrows. Now I missed one thing, it is this. So you have to write all the components of the accelerations like this. For P1, you need to include these two. For P2, you need to include these two. Right? Now we'll write the equations. Now how many variables and how many count the number of variables means number of tensions and accelerations. On the other hand, number of moving objects, one, two, and three. So three. That means you can apply at most three equations without reactions getting involved. Three. So how many variables? Two accelerations, simple if and capital F, and one tension. So we are fine. Right? We are in a good shape. So we'll apply, we'll start from the simplest one. Apply F equals ma for P2. No forces because weight and this, there's a force, I'm sorry. Weight and this is the reaction, there's a tension, T. Mass is 2m. Remember that the mass is 2m. Mass of the wedge is 3m. So what is the acceleration? Simple F minus capital F. Simple F minus capital F. I'll take this as 1. Now apply an equation for P2, P1. Again, okay, there are two forces. mg. Now we are applying along the plane, this side. So it is this 90 minus alpha. This angle is 90 minus alpha. Therefore, you have mg cos 90 minus alpha, which is mg sin alpha. T is in the opposite direction. S is not involved. It is in the perpendicular direction, and that's why we are applying it in this direction, just to eliminate S1. Mass is m, and the acceleration component, simple F, it is in this direction. This angle is alpha, therefore capital F cos alpha. It is in the other direction. I told you earlier, Whenever you have t, you better get that eliminated. And at the same time, we need one more equation. We apply that t equation for the system. T will not be involved in that t equation. Therefore, you better replace t right now. You can add these two. I'll take this as equation 2. Now from 1 and 2. Or you can say from equation 1, then you replace this guy by, I can do it like that. Now last time I didn't eliminate t at the beginning. Now from 1, this is mg sine alpha. Okay, when you add these two, it will go away. This is 2a. Okay, no, not that. I'm sorry. You can do that. You replace t by, I mean, without labeling this equation, I cannot add these two. Instead, I can replace t by 2m times simple F minus capital F. So I can do that. Right? Now I can divide everything by simple M. Right? Now, how can you do this? Take the variables to one side. We can do it slowly. Now, if you take this to the other side, it will appear like this. Now, 2f plus f, 3f, 3 simple f. From these two, you can pull out minus sign and f, capital F. I mean, from these two, you have plus 2, 2 plus cos alpha. Minus f is common to everything, these two. So you get 2 plus cos alpha. I label this as equation 2. Now you need a third equation, that's for the system. Now no forces will be involved in there. Why? These weights will go away, R will go away because we apply it horizontally. That's what, uh, we applied horizontally because just to eliminate R. And the other reactions are internal reactions if you take the entire system. Therefore, S1, S2, and T will automatically eliminated. So you get just 0. Now, here you have 3m. Mass is 3m. Its acceleration is capital F. It's like sigma ma. You consider every particle and get the product of m times a like that. Now, for this, no, I'll go for 2m. Sorry, m. For this, capital F minus simple F cos alpha. This is also alpha. Capital F minus simple F cos alpha. You can even see that from here. If you apply the equation for this, capital F minus simple F cos alpha. Here, for the third one, P2, it is capital F minus simple F. You can see that. If you apply, since you apply the equation to this side, capital F minus simple F, its mass is 2m. Now you can first divide it by simple m. So you get 3f, 3 capital F, plus when you divide it by m, you get simple F minus, sorry, capital F minus simple F cos alpha. This is 2 times capital F minus simple F. So 3 plus 1, 4 plus 2, 6 capital F. Then from these two, you can pull out simple F. You get, and minus simple F. So you get 2 plus cos alpha. This is 3. Now we don't need 1 anymore. Uh, Using 2 and 3, you can find capital F. I better go one step ahead. I can eliminate simple F using this. At least I can have this form, and I need to find capital F, right? First, I'll eliminate simple F. Now, from 3 and 4, if you replace simple F by that, the only variable left in this equation would be capital F. So from 2 and 3, okay, what I'm doing is this, what I'm planning to do. I want to replace simple F by capital F. So G sin alpha will be there. So G sin alpha is equal to 3 simple F. Now for simple F, I write this 3 simple F. Now you have this minus 2 plus cos alpha times capital F. 2 plus cos alpha times capital F. Now what you can do is that you can multiply everything by 2 plus cos alpha. Here, when you multiply this by 2 plus cos alpha, it will go away. It leaves you with 18f minus, when you multiply it by 2 plus cos alpha, you multiply this by 2 plus cos alpha, that's what you get. Now, from this, you can eliminate capital F. Or not eliminate, I'm sorry. You can pull out capital F. 18 minus 2 plus cos alpha quantity squared. Now divide. Now you have the acceleration of the wedge. Now with that, right? If you use this equation again, now we know what capital F is. Then you get simple F. That you substitute capital F there. Now from equation 3, simple F is, okay, 6 over 2 plus cos alpha times capital F. Now this is capital F. G times 2 plus cos alpha times sin alpha. I will get this refilled as quickly as possible. Downstairs you get, or in the numerator you get this. Just told you, no, you may be unable to see it clearly. I'll erase this. Okay, from 3, you have this. So I mean, in 3, this is what you have. So 6 over 2 plus cos alpha times f, right? This is f. G times 2 plus cos alpha, then you have sin alpha divided by 18 minus 2 plus cos alpha quantity square. Now you can cancel these two, right? Now what you get is 6g sin alpha divided by 18 minus this. So this is the acceleration of P1 relative to the wedge. Okay, we are done with that. Now you take this down. We'll do another problem. Okay, we'll do this before taking a break. Uh, okay, in this problem, uh, to solve something, we have to find sufficient number of equations to find the time taken for P to collide with the table. Now, so at this point, the the height difference, so they are in fact h distant apart. Now, you have to uh, first figure out the accelerations. I'll take this acceleration as F1. This is F2. Uh, this will definitely move in this direction. I'll take it as capital F. Now, this is purely, basically, an acceleration related to the Earth. This is also an acceleration related to the Earth. So we can first take care of this. So acceleration of Q or 4m, the wedge, related to the other way around. Acceleration of Q related to the Earth is this. Then the acceleration of P2 related to the Earth, that is F2. The acceleration of this F1 is simply related to the Q. So this is acceleration of P1 related to Q. It is in this direction. Now that's not what we want. We want to find the acceleration of P1 related to the Earth. So like in the case of vector notation, I write Q in the middle. Now in this case, it is this, the acceleration of Q related to the Earth is this. So there are two components. Now we'll do the problem. Here we don't have to solve the equation. We have to find sufficient number of equations to find the time taken for P2 to collide with the table. Now we'll draw a diagram, a clear diagram. With more details and the forces involved. This is, I guess, 2m, right? So its weight is 2mg. Here the weight of this is mg. There's a reaction. Weight of the wedge is 4 mg. And there's a reaction R between the table and the wedge. This is fixed to the, I mean, it's pulley is fixed to a certain point on the ceiling. You cannot take it as a system. System is this, because it's attached to something else, right? Then the tensions. This is P2. This is P1. Now we'll mark the accelerations. Tension is, we are done with the tension. We are done with the reactions. Here, this reaction is not necessary. Don't take it. This is not a moving object. Now, the acceleration of this is F. Use a double arrow just to avoid confusion. This has two components. This F1. Then the acceleration of this is F2. Basically, that's it. Now we'll write the equations. When you write the equations, I have to indicate the height here. Now, we need to find F2. We don't have to find, but we have to write sufficient number of equations to find F2. Now count the variables. We don't care the heights and stuff like that. We simply find the number of accelerations and number of tensions. There's one tension. This is smooth. I mean, these are smooth pulleys, and there's only one tension. There are three accelerations: capital F, simple F1, simple F2. So three accelerations plus one tension, altogether four. And there are three moving objects. Number of equations uh, you can get without getting these reactions involved should be the number of moving objects, that is three. However, we have four variables, three accelerations plus one tension. So we are missing one equation. That means we have to use we have to use derivatives to find an extra equation. The reason is that there's some connection between these accelerations, but we don't see what it is. So how do you come up with this? Okay, we'll take this as the length of the string can be divided into three, the straight portions of the string. You better use some simple x, simple y, or x1, x2, x3, like that. I take this as x1 because it is associated with f1. I take this as x2 because it is associated with f2. I take this as x. Now the straight portions of the string should be a constant. So we have to use derivatives to come up with an extra equation. That means, x2 plus x plus x1 is a constant. Now, to get accelerations, you can straight away differentiating twice. Because if you do it once, you get the velocities. We don't need velocities. Twice with respect to t. These two, the initial first letter of two, this is t, the time. Or you can see something like this with time, to time. Now, if you differentiate this twice, you write it as x2 double dot. This will be x double dot. This is x1 double dot, and this is 0. Right? You can see, if you see that, okay, this is moving this way. So with the positive direction of F2, now we have to find the relationship between x2 and F2. With the positive direction of F2, as indicated, x2 is increasing. So that means it has a positive relationship. Now with the indicated direction of F1, x1 is increasing. So it has a positive relationship. However, with the indicated direction of capital F, this is fixed. This is moving closer to the pulley, this pulley. That means X, the distance between these two pulleys approximately, these two pulleys will be reduced. So with the indicated direction, if this is moved, simple X will be reduced. So that has a negative relationship like this. Now we'll substitute those here. F2, this is minus F1, sorry, minus capital F. This is plus F1. Or you can write it like this. F1 plus F2 is capital F. There's a relationship between these accelerations which we didn't see at the beginning. So you have one equation. Now that the requirement of the extra equation is done. Now you have one equation. You need to have three more. Just apply Newton's law for this system. Sorry, for this object particle, for this particle, and for the system. We'll later identify what kind of a system we are using here. Now we'll apply F equals Newton's law for this. So we'll apply F equals ma in this direction, in the direction of its acceleration. That would be better. For P2. So 2mg is in this direction, minus t is in the opposite direction, is equal to 2m times F2. So that's our second equation. Now we can apply an equation to P for P1, Newton's law for P1, but this way. Just to get rid of S1, you have to do it like that. Now we'll apply it in this way. For P1. If you do that, what are the forces? This is 90 minus alpha. So mg cos 90 minus alpha means mg sin alpha. T is in the opposite direction. Mass is m. Here the mass is 2m. Here the mass is m. Times the acceleration. Now there are two components. F1 is in the direction of application. F1. This you have to resolve it. This is alpha. So F1 cos alpha. Minus, sorry, not F1, capital F cos alpha. So we don't have to solve them. So we label this 3. We need one more. So we have to apply an equation for the system. Now it's hard to find the system because this is not involved in the system. So you can take a piece like this. Because how can you differentiate between this pulley? Because there's at the pulley, if you just take the pulley itself, it will be like this. So there are two tensions here. There will be a force acting on this. So if you break the system here, then you have to consider force like that. The force acting from the pulley onto the string. So it's weird. So take that into the system. Then those are internal reactions. You don't have to worry about it. Break it somewhere here. Now, basically, the main object here is the wedge. So apply F equals ma for the system. Now, what are the forces? These will not be involved. S will not be involved, and because S1 will be an internal reaction, the only force is this T. T is equal now sigma ma. Means for each piece, you write m times a like that. Here the mass is 4m. Its acceleration is f. Now for this, its mass is m. The accelerations are okay. You have f to this side, and F1 can be resolved. If you resolve it in this direction, this angle is alpha. So minus F1 cos alpha. Now, if you solve these four, there are how many variables? F1, F2, capital F, and T. So you should be able to, like we did earlier, you should be able to find capital F. If you want, I can show it how to solve, but not necessary here. So you can solve this for capital F. Or in the same fashion, you can solve it for F2. Now, if you find F2, now you can find the time taken for this to hit the table. Now it is like this. You have an object whose acceleration is F2, which is exactly h away from the table. I mean, you don't have to draw an extra diagram. Everything is there. Now, how to find the time? Initial velocity is zero because you release the system. Initial velocity is zero, so you need to find the height. Sorry, height is given. You have to find the time. So it should be s equals ut plus half at squared for P2. Then height is h. Initial velocity is zero. Its acceleration is f2 t squared. So 2h over f2 and get the square root is t. I'll take this as 5. Now, once you know f2, you can find t. So you can find f2 using these four equations. That means you have to include a statement like this. By solving 1, 2, 3, and 4. Sorry, wrong. 4 and 5. The required time taken. Whether the, yeah. Others you have to be too lengthy, too wordy, right? The required time taken can be found. OT can be found, right? So that's how you have to answer something like that. Okay, you take that down and then we'll go for a break. Half an hour, right? Okay, we'll take up one more problem and we can wind up with this. Hmm. Now, in this case, there are two wedges involved in this problem, and the this wedge is fixed. It's stationary. This can move, so there are altogether three movable objects or three moving objects. So we can get at most three. I mean, you can apply F equals ma or Newton's law three times, exactly, or at most three times. Uh, so we need to again find the equation, sufficient number of equations to find this wedge to collide with, I mean the time taken for this wedge to collide with the stationary wedge. Now we'll see how to do this. First, let's mark the accelerations. Here, don't try to be too detailed here. This is P1, this is P2, both are equal to M. Okay. Now, the acceleration of this, I would say F1, it is straight away an acceleration related to the Earth. This is an acceleration related to 2m. Now, even though these two are attached to the two ends of the string, this is moving. Therefore, F1 is not equal to F2, right? Now, the acceleration of P1 related to the Earth is, this angle is alpha. I forgot to give that. They are identical, two identical wedges. Uh, it is this. Again, if you take this acceleration of 2m related to the Earth is this. Now, the acceleration of P2, this is relative to 2m. It's not an acceleration relative to the Earth, right? Please note that fact. So it is F2. Now, we cannot apply Newton's law with this setup for P2 because we always, in Newton's law, the acceleration A is the uh, acceleration related to the Earth. Therefore, we need to know that. Now, this is F2 and the acceleration of 2m related to the Earth is this. Now, we are done with that. Now, we'll write equations. I'll do it around the figure. Then it's easy to capture everything uh, in one screen. So I'll do it like this. Huh? I'll do the problem around the diagram. But when you copy that down, you do it one below the other. Draw the diagram and list equations right below this. I mean, one below the other. Now, this is fixed. The weight is mg. Here we need the reaction. I label it as S2 because the object is P2. The particle is P2. Here we don't care what the forces acting on the fixed wedge. I'll take this one, which is the reaction on the mass or on P1, on the particle on P1 by the wedge. So basically that's it. Now the accelerations. This is capital F, and also we have to indicate the tension. Right? Now, this has two components. P2 has two components. One is F2 and the other is capital F. So basically that's it. Now, initially this is L. Now the problem we have is how to write the equations. There are three moving objects. Therefore, you can apply three Newton's law. I mean, Newton's law three times. So you get three equations. But how many accelerations and tensions are there? Oh, sorry. This is F2, this F1. So F1, F2, and capital F. Three accelerations and one tension. So four variables, but we have three chances of applying Newton's law. So that means we need to come up with an equation, extra equation using derivatives. Again, I use the same notation. This length as x2, this is x, this is x1. We have to obtain the extra equation because we are one equation short otherwise. So x1 plus 6 plus x2 are the straight portions of the string. Constant. If you take the portion of the string which doesn't touch with the pulleys is constant. Now differentiating twice. Time. Now this will be x1 double dot. This is x double dot. This is x2 double dot, which is equal to 0. Now look at the directions of each acceleration and see what the effect of that particular acceleration on the given variable x1, xo, x2. Now if you take f2, if this one takes the direction indicated by f2, x2 increases. So it's a positive relationship. If you take this as well, now if this particle takes the direction of f1, x1 increases. So it's a positive. It's a positive relationship. However, if capital F takes this direction, and since this is fixed, it will decrease x. Therefore, x double dot is minus f. It has a negative relationship. Now we'll plug in these things here. So this is f1, this is minus f, this is f2 is equal to 0. So that's our first equation. Now we need to get three more. Now this is the simplest. So we'll apply, this is P1. We'll apply a Newton's law to P1 in this direction. For P1. You get this this alpha, this also alpha. So if you resolve it, this is 90 minus alpha. So cos 90 minus alpha is sine alpha. So it is mg sine alpha minus t is m times the acceleration. It is simply f1. It's the acceleration related to the earth. So I'll take this as equation 2. Now I can apply an equation to this. P2. So again, it is like this. You get this is again mg sine alpha minus t, the same tension, uh, m times f1. Here f1, sorry, here f2. I mean, here we are applying it in this direction, so f2 is positive. You have to resolve this f in this direction, and this angle is alpha. So it is capital F cos alpha, and it's negative. This is the third equation. Now, we have to go for the fourth equation. We can consider system. Now here, if you take the entire system, this is fixed. So I have to now write something. I have forgotten this reaction. R. Now, clearly you have to get rid of R when you write the equations, because uh, if you have R in the equation, then you have you need one more equation to get it, to solve for that. Therefore, to get rid of R, you have to apply the equation horizontally. Now, this is not in the system because it is attached to some other to the table or somewhere. Therefore, those reactions are unknown. So this cannot be included in the system. So if you take this in the system, if you apply it in this way, S1 will appear. Therefore, the only hope is that you better consider system like that. While you have to involve this pulley for the system, because otherwise we have to even compute those forces, the force on the pulley. So therefore, you have to include that. Now, if you apply, now you have to apply this horizontally to get rid of R for the system. Okay, R will go away, these weights will go away. This is an internal reaction. This T will be there. T. The masses, it should be sigma ma. For 2m, the acceleration is F of m. F is there in this direction, and you have to resolve it like F2 cos alpha. It's minus. And that will be your fourth equation. So by solving these four, you can find the accelerations and the tension. In particular, you can find capital F, the acceleration of the wedge. Now we have to find the time taken for this wedge to collide with this. Like, for example, if you want to find the velocity at which, velocity when this collides with the stationary one, then you have to apply an equation of motion accordingly. Since the length is given, you have to apply an equation containing the final velocity and the distance. So v squared is equal to u squared plus 2as. But in this case, we have to find the time. When the distance is given, you have to apply c equals ut plus half at squared. If you want to find the final velocity, you have to apply half sorry, apply V squared is equal to U squared plus 2AS. But in this case, this is the equation you need to apply for 2M, means for the wedge. So length is L, the displacement is L, initial velocity is 0, this is half, this is capital F T squared, right? So T is the square root of 2L over F. So by solving is 5. It's in fact wedge Q. Okay. So basically, that's it. Hmm? Okay, next time you better get your hybrid card active before next Wednesday, right? Uh, this time everything happened all of a sudden. Okay, now this is the solution for this, and I think that's good enough for today. So we'll do some more problems from this and certain like shorter version involving with certain pulleys, no wedges, just pulleys. So we have to go through like few more examples next day, and next day we are going to finish this section. Hmm. Uh, then probably we can start new section, and I'll tell you what it is, what it will be uh, next week. Okay, right. So I'll okay. Have a nice weekend, and have a nice week, and you better do your paper. I mean, this time we don't have paper, but next week we have. This week we don't have paper. Paper. I'll give you paper 19 next week. Right? Okay.